We've seen what neural networks are, how to train them by gradient descent, and how to compute that gradient by backpropagation. Now, in order to scale up to larger and more complex neural networks, we need to make our computations as efficient as possible. And we'll also need to simplify our notation. There's one insight that we're going to get a lot of mileage out of. When we look at the computation of a neural network, we see that most operations can be expressed very naturally as those of linear algebra. For instance, the multiplication of weights by their inputs is the multiplication of a matrix of weights by a vector of inputs. In a vector by matrix multiplication, there is an element in the matrix for every combination of an element of the input vector and an element of the output vector, and the same is true for the operation of our first layer. The addition of the bias can be expressed as a vector of bias parameters. The nonlinearities can be implemented as simple element-wise operation, a function that is applied to every element of the vector independently, and in the same way we can express the operation of the second layer. This perspective buys us two things. First, our notation becomes extremely simple. We can describe the whole operation of our neural network with this simple equation. This expressiveness will be sorely needed when we move on to more complicated networks. The second reason is efficiency. The biggest computational bottleneck in a neural network is the multiplication of the layer input by the layer weights, the matrix multiplication in the notation of the previous slide. This operation is more than quadratic, while everything else is linear. We can see that in our pseudocode because we have one loop nested in another. Now, matrix multiplications and other tensor operations like it can be parallelized and implemented efficiently, but it's a lot of work. Ideally, we'd like to let somebody else do all that work, like the implementers of NumPy, and then just call their code to do the matrix multiplications. This is especially important if you have access to a GPU. A matrix multiplication can easily be offloaded to the GPU for much faster processing, but for a loop over an array like we've used here, there's no benefit to doing it on the GPU. This principle is called vectorizing, taking a piece of code written in for loops and getting rid of the loops by expressing the function as a sequence of linear algebra operations. Without vectorized implementations, deep learning would be painfully slow and GPUs would be useless. Turning a naive loop-based implementation of an algorithm into a vectorized one is a key skill for deep learning researchers and programmers. Here's what the vectorized forward pass looks like as a computation graph. Instead of specifying each scalar value involved in the operation of the neural network as a single node, we now take vectors for the input, for the hidden layer, and for the output, and represent these vectors as single nodes. In pseudocode, it would look like this. And when you implement a network like this in NumPy, it looks almost exactly the same. So far, so good. The forward pass of our neural network is easy enough to vectorize. Of course, we lose a lot of the benefit of vectorizing if the backward pass, the backpropagation algorithm, isn't also expressed in terms of matrix multiplications. So how do we vectorize the backward pass? That's a question we'll answer in the rest of this video. On the left, we see the forward pass of our loss as a set of operations on vectors and matrices. To generalize backpropagation to this view, we might ask if something similar to the chain rule exists for vectors and matrices. Can we define something analogous to the derivative of one matrix over another? And then can we break this derivative apart in a product of local derivatives, possibly giving us a sequence of matrix multiplications? The simple answer is yes. There are many ways of applying calculus to vectors and matrices, and there are many chain rules available in these domains. However, if we try and work out backpropagation this way, things can quickly get a little hairy, so we need to tread carefully. The derivatives of high-dimensional objects, like matrices and vectors, are easily defined. For any given function from a matrix to a matrix, we simply take the derivative of every number in the input over every number in the output, and we arrange all possibilities into some logical shape. For instance, if we have a vector-to-vector function, the natural analog of the derivative is a matrix with all the partial derivatives in it. This is called the Jacobian. And for instance, at position 1, 2, it contains the derivative over the second element of the output with the first element of the input. Since there are 2 outputs and 3 inputs, the Jacobian is a 2 by 3 matrix. This principle extends fairly naturally to a lot of situations, but once we get to matrix by vector operations or matrix by matrix operations, we run into trouble. The only way to logically arrange every input with every output is a tensor with a dimension higher than 2. As we see, if we could come up with this kind of chain rule, even for our simple multilayer perceptron, one of the local derivatives is now a vector over a matrix. The result, the analog of the Jacobian, could only be represented in a 3 tensor. There are 2 problems with this. If the operation has n inputs and n outputs, then we are computing n to the power of 3 derivatives, even though we were ultimately only interested in n to the power of 2 of them, which are the derivatives of the loss with respect to the weight, w. In the scalar algorithm, we only ever had 2 nested loops, an n squared complexity, and we only ever stored 1 gradient for 1 node in the computation graph. Now we suddenly have n cubed complexity and n cubed memory use, while we were supposed to be making things faster. So clearly this is not going to work. The second problem is that while we can easily represent a 3 tensor, there's no obvious default way to multiply a 3 tensor with a matrix or with a vector. In fact, there are many different ways. So when it comes time to multiply all these local derivatives together, we wouldn't know what to do. In short, we need a more careful approach. The idea of simply using the chain rule to break apart the global derivative into local derivatives doesn't work for us here. We can still use the chain rule to work out a backpropagation algorithm, but we need a slightly different approach. In order to work this out, we make the following simplifying assumptions. The computation graph that we're interested in always has a single scalar output, the loss, and we are only ever interested in the derivative of the loss with respect to all the parameters of our model. In short, this is always what we're going to be working out. The derivative of a scalar loss with respect to a tensor of any dimension. And that means that in our earlier diagram, we are always in this column. The input of our function is a tensor of any dimension, 3 dimensions or even more, but because the output is always a scalar, we can always represent the set of derivatives that we're interested in, the derivative of the loss with respect to one of these inputs, as a matrix of a logical dimension. Note that assumption 1, that the computation graph always has a single scalar output, does not mean that our model can only ever have a single scalar output. Our neural networks can have any number of outputs of any shape and size. We can make neural networks that generate images, natural language, raw audio, or even video. In fact, these are some of the most interesting applications of deep learning, so we definitely want to be able to do this. However, the loss we then define over the outputs of the neural networks, that needs to map all of these outputs to a single scalar value that tells us how well we're doing. The computation graph is always the model plus the computation of the loss. Now, let's get back to this gradient. We have some tensor W, let's say a matrix, and that influences our loss. We are interested in the gradient of the loss with respect to every single element of this matrix. This quantity is called the gradient of L with respect to W. It's simply a collection of all derivatives of the loss with respect to every single element of W. The standard notation for this gradient is shown here. This symbol is pronounced as nabla. A non-standard assumption we make in deep learning is that the gradient has the same shape as the thing we're taking the gradient with respect to. Normally, the gradient is defined as a row vector so that it can operate on a space of column vectors by matrix multiplication. In our case, we're never interested in multiplying the gradient by anything. We don't think of the gradient as an operator. We only ever want to sum the gradient of L with respect to W to the original matrix W in a gradient update step. For this reason, we define the gradient as having the same shape as the tensor W with respect to which we are taking the derivative. For instance, in this example, we can think of W as a 3 tensor, and then we say that in this gradient, the element ijk is the gradient of the loss with respect to element ijk of the matrix W. With these rules, we can use tensors of any shape and dimension and always have a well-defined gradient. Now, this standard gradient notation isn't very suitable for our purposes. It puts the loss front and center, but that will always be the same in all cases. We are always taking the gradient of the loss. The object that we're actually interested in that changes from case to case is relegated to a subscript. It's W. Also, it isn't very clear from this notation what the shape is of the tensor that we're looking at here. For this reason, we'll introduce a new notation. This isn't standard, so don't expect to see it anywhere else, but it will help to clarify our mathematics a lot as we go forward. It looks like this. We've put the W front and center, so it's clear that the result of taking the gradient is also a matrix of the same shape as W, and we've removed the loss, since we assume that we are always taking the gradient of the loss. You can think of the nabla a little bit as an operator like a transposition or taking an inverse. It turns a matrix into another matrix, or a vector into another vector, and so on. The notation works the same for vectors. B nabla represents the gradient of the loss with respect to all the elements of B, and it's a vector of the exact same shape as B. And even for scalars, we can also apply the nabla operator. It simply refers to the single scalar derivative of the loss with respect to scalar y. When we refer to a single element of the gradient, we will follow our convention for matrices and use the non-bold version of its letter. Element ij for the gradient of W is the same as the gradient for element ij of W. So with this notation in our back pocket, we can start to develop a vectorized version of the backpropagation algorithm. The basic recipe is given in these 2 points. We work out scalar derivatives first on pen and paper, and then we vectorize. And we will do this primarily using the multivariate chain rule. And with the chain rule in hand, we simply start at the top of the network at the loss and work our way backwards, accumulating the gradients. Here's an example of what that looks like for our multi-layer perceptron. We start with the node directly below the loss, y, the output of the network. For the sake of generality, we'll think of y as a vector, so that our network could also have multiple outputs. So what is the gradient for y? Y is a vector, so the gradient for y is also a vector with the same shape. The principle tells us that we should start with scalar derivatives. Let's pick one element of this gradient vector, element I, and see if we can work out what that should be. By definition of the gradient, the ith element of y nabla is simply the derivative of the loss with respect to element yi. The loss we can fill in because we know the definition of the loss. And this is yk, the kth output of the network, minus tk, the kth element of the target vector that we get from the data. We square this difference and we sum it over all k. That's our loss function. And we want the derivative of this value with respect to the element yi. The basic rule of differentiation is that we can take this sum out of the differentiation and sum over the various derivatives. Applying the chain rule to the element inside the sum, we get this derivative. And looking at this sum, we note that the thing we are taking the derivative for, yi, will only appear in one term of this entire sum. So this thing here will be 0 whenever y isn't equal to k. So all of those sums are 0 and we can remove them, and the only sum that remains is the one where I is equal to k. So we can set all of these k's equal to I and remove the sum symbol. And in that case, yi here is equal to yi here. So this derivative becomes 1, and all that remains is this part of the sum. So what has this brought us? We now know that this vector that we're interested in, the ith element of that vector, is computed by this expression. This is what we mean by working in scalar terms. Now that we have the scalar expression, we can ask what the entire vector looks like and see if we can vectorize that. So the whole vector y nabla is simply the collection of all of these yi's put together in one vector. And for every element of that vector, we can compute this function here, which gives us this vector over here, which we can compute as follows by simple linear algebra. So that gives us a vectorized expression of how to compute the gradients for this node in our computation graph. This can be implemented directly in NumPy by subtracting this vector from this vector, and we can let NumPy deal with a parallelized implementation to make sure that this is computed quickly. In short, we have gotten rid of the for loop in our backpropagation algorithm. in the computation of the gradients for y. Now, to see the backpropagation in action, the accumulation of what we've computed, to see that in action, let's move one step down in the computation graph and see if we can work out the gradients for v. V here is a matrix because we have an input vector h and an output vector y. And we apply the same recipe. We start in scalar terms. We pick one element of this matrix, Vij, and we see if we can work out the derivative for it. What's the derivative of the loss with respect to element ij of the matrix? Now, the first thing we have to contend with is that in this computation graph, between the loss and this input value Vij over here, there are lots of intermediate values y. So if we want to apply the chain rule to break this up into a loss of L with respect to y times a loss of y with respect to Vij, we need to go through all these different paths of the computation graph. Now we know how to do this. We can simply use the multivariate chain rule. And in this case, it tells us to sum over all of these paths. So for every path, every element of the intermediate vector y, we apply the chain rule through that path. The derivative of L over Vij is the derivative of L over yk times the derivative of yk over Vij, and we sum that up for all elements of the vector y. Now we can fill in what we already know, and the first thing to note is that this quantity here, this first factor, the derivative of L with respect to yk, we've already computed in the last slide. So we don't need to do that again. We can just assume that we've computed this, and we are simply referring to this as the kth element of this y nabla vector that we computed in the last slide. That's given. All that we need to do now is work out what this factor should look like. As before, we simply look at the numerator and fill in its definition. Here the numerator is yk, and the definition of yk is the kth element of this matrix multiplication that we compute in the second layer, v times h plus c. This results in a vector, and the kth element of that vector is yk. And what we're trying to do here is to reduce this bit of linear algebra to purely scalar operations so that we can apply the rules that we know from computing the scalar derivative. We can break this up in two steps. First, the kth element of the vector that results from this sum is simply the kth element of this vector plus the kth element of this vector. So we see here ck plus the kth element of the vector that results from this matrix multiplication. And the kth element of this vector here is simply the dot product of the vector h and the kth row of the matrix V. This term c does not contain Vig, so this part we can remove from the derivative. And the dot product we can simply express as a sum of the element-wise products of these two vectors, where we sum over the index L. And with that, we have reduced everything to a function that is purely scalar, so we can apply simply what we know from taking scalar derivatives to work out the derivative here. Step 1, we take this sum over L and move it all the way outside the derivative and outside the multiplication by yk. And in step 2, we see that this element that we're taking the derivative for, Vij, only appears above the line if k is equal to I and L is equal to j. So in all the terms of this sum, all of them are 0. We can remove all of them except the one term where k is equal to I and j is equal to L. So to express that remaining term, we simply take all the k's, replace them with i's, take all the l's, replace them with j's, and we get this expression here. And finally, this is just one number multiplied by one other number, and we take the derivative of that with respect to the first number. So those disappear, and we end up with hj. So now we have a scalar expression for what this particular derivative here should look like. One element of the matrix phi nabla, we know what it should look like. So now to vectorize, we write down what the whole matrix should look like. It should be the matrix that contains this quantity for every element ij. And with a little creativity, we can see that if we take the outer product of the vector y nabla and multiply it with the transposed vector h, that gives us exactly the matrix that we want. So note the general trend here. We work out the individual elements using the rules that we know for scalar derivative taking. And then, with a little creativity, we try and work out a way to compute the whole matrix of all of these derivatives efficiently. So again, step by step, to work out a gradient x nabla for some x, we write down a scalar derivative of the loss with respect to one element of x. We use the multivariate chain rule to sum over all the outputs that are in between us and the loss. We work out the scalar derivative, and we vectorize the computation in terms of the original inputs and the gradient for the node that is directly above us in the computation graph. Since this is an important principle to grasp, and it will come back in the homework as well, let's keep going until we get to the other set of parameters w. We'll leave the biases as an exercise. For the gradient for h, most of the derivation is the same as before. We start with a single element of h nabla, in this case the ith element, which represents the derivative of the loss with respect to element I of vector h. We apply the multivariate chain rule, and again the first factor is an element of y, which we've worked out before. We fill in the definition for the part above the line, which again is the same matrix multiplication as we saw before. The kth element, again, we can work out as before, as the dot product of a row of matrix V and the input vector h. We work the sum out of the derivative and combine it with the other sum. But at this point, note that we cannot eliminate all but one of the terms of this sum. This derivative is non-zero whenever I is equal to L. So all the terms where L is not equal to I, we can eliminate from the sum, and we can express that by setting all the L's equal to I and eliminating the indexing over L, but we still have an indexing in the sum over K. Continuing with this sum in place, we can work out this derivative by cancelling the hi's against each other, which leaves us with this expression for the scalar derivative for hi. This is the quantity that we need to compute for every hi. So to vectorize, we are looking for a vector h nabla, where each element in that vector is computed by this expression. Now at this point again, vectorizing takes a little creativity, so we need to study what we have here. Now this we can read as a dot product between a vector y nabla that we're given and the ith column of V. Here's what that looks like in a matrix multiplication diagram. And we see from this diagram that if we take the transpose of yk and multiply it by V, we get a row vector with all the values that we want. Since we need a column vector, we then transpose again. And cleaning that up, we see that what we're actually interested in computing is the multiplication of the transpose of V with this vector of gradients for y. Moving back down, when we analyze k, remember that we already have the gradient over h. This means that we don't need to apply the chain rule for anything above h. We can draw this scalar computation graph here and work out the local gradient of k in terms for the gradient for h. So this is the gradient we're interested in. This is what we get when we apply the multivariate chain rule. And again, the factor on the left we have already. We don't need to work this out. We're only interested in this local scalar derivative. We fill in above the line the definition of hm, which is the sigmoid applied to node km. And in this sum, again, we can see that the quantity below the line ki only appears above the line in one term in this sum, when I is equal to m. So we can get rid of the sum symbol and set all m's equal to I. And what we see here is that the factor on the right becomes a very simple scalar derivative for the sigmoid function with respect to its input. And we know the derivative of the sigmoid function already, which is the output of the sigmoid function times 1 minus the output of the sigmoid function. These quantities we've already computed in the forward pass. They are hi and 1 minus hi. So we can simply remember them during the forward pass and apply them again here during the backward pass. So this is the quantity that we're looking to vectorize. We're looking for a vector k nabla, where the element k nabla I is computed like this. And since the ith element of k only depends on the ith element of the vector h nabla and the vector h, we can simply express this as an element-wise multiplication of these three vectors. Finally, we've made our way to W. We're looking for the gradient for W, and again we'll focus on a single scalar element. The situation here is exactly the same as we saw earlier for V, matrix in, vector out using matrix multiplication. So we should expect the derivation to have the same form, and indeed it does. We apply the multivariate chain rule, the gradient for the output vector is given, we fill in the definition of Km, express it as a dot product, move the sum of the dot product out in front, and isolate the only term that is non-zero, which results in this scalar expression. That means that this is what we're looking for the vectorized version of W nabla, which again we can compute as an outer product as we did before. It takes a little while to work all of this out, and on pen and paper we're doing a lot of complicated stuff, but once the time comes to transfer all of these ideas to code, we see that we end up with very simple pseudocode. All we need to take from our paper into our code is these vectorized implementations of the gradient for these various nodes. So that's the idea of vectorizing. It makes notation simpler and computation faster. Vectorizing the forward pass is usually very easy, and for vectorizing the backward pass for a given network, there is a standard recipe. We work out the scalar derivatives, accumulate using derivatives we have already worked out for the upstream part of our network, and then vectorize once we have the solution in terms of our scalars.